All right, another exercise from 9.5 is 9.525, which has multiple parts and ends up proving something that's very useful, namely that the order of an element is equal to the size of the cyclic subgroup generated by the element. So let's go through this step by step. First of all, we're assuming A is a group element, and the order of A is equal to n. What does that mean? That means that n is the smallest positive integer such that a to the n equals id. That's the definition of the order of a group element. Remember, order of a group element is different from the order of a group. Down here, for instance, we have the order of A. That's the number of elements in the set A. Here, we're just, when we talk about the order of an individual element, that's the smallest positive integer such that a to the n is the identity. Okay. All right, so let's start off with this part A. Part A says, show that for any integer m, and this positive or negative integer, a to the m equals a to the mod of mn. Now, you should recall that mod is defined in terms of remainder. Mod is the remainder when you divide m by n. Mod is what's left over. So what does that mean? That means that any integer m is a multiple of n plus remainder, right? Multiple of n plus remainder, right? So that's just what I'm right here. So by the definition of mod, m is equal to kn plus mod of mn. It's always going to be true for any integer m and any positive integer n. Right? And here k is some integer. K could be positive or negative. All right, so let's use this to express a to the nth power. So I just substitute what m is. M is kn plus mod of mn. Then I do some exponent rule stuff. I can break the sum of exponents into two separate terms. Then here's the product of exponents. I can write it as a repeated exponent. And then because the order of a is n, I can write a to the n to the k as 1 to the k. And actually that should be id to the k. So let me change that. It should be id to the k, because we're not necessarily working in the integers. So let's change that. id to the k. That's a to the mod mn. Now, if you take id times a mod mn, that's just going to give you a mod mn. All right, and that's what we wanted to show. We start out with a to the m. We start out with a to the m. We ended up with a to the mod mn. So that finishes the proof of part A. All right, now part B. Part B says, suppose I have this set. This set has n elements, and I want to show that the orbit of A is contained in big A. In other words, or the cyclic subgroup generated by A is contained in A. And I'm going to use part A. All right. So what I want to do is show that any element of this orbit is also an element of big A. And I use part A. So here's the proof. It comes pretty directly. Suppose x is in the orbit of A. Then x equals a to the L for some integer L. That's the definition of the orbit of A. So x is equal to a mod Ln. All right, because that just follows from what I had up here. Here I had m. I had a to the m is equal to a mod mn, so a to the L is equal to a mod Ln. Okay. But the mod of Ln is between 0 and n. So in fact, a to the mod Ln is one of these numbers here, because the exponent is between 0, which would give me the identity, and n minus 1, which gives me the largest power. So that tells me that x is, I wrote it this way, x is a to the q, where q is in this set, and that's exactly what I wanted to show. So that gives me part B. All right, let's look up at part C. Part C says, prove that the order of the cyclic group generated by A is equal to the order of A. So in other words, number of elements in the cyclic group of A generated by little a is equal to the order of big A. All right. So, all right. So what I need to show, in fact, or how I can show this is if I show these two sets are the same, if I show that the cyclic group generated by A and big A are the same set, then they have the same order. So that's the strategy I'm going to use. That in fact the cyclic group generated by little a and big A are the same set. Now, part B showed me that the cyclic group generated by little a is contained in big A. So all I need to do is show that big A is contained in the cyclic group generated by little a. And that's what I'm going to do here. So we've shown, as I said, that the cyclic group generated by little a is contained in big A. But on the other hand, every element of big A is an element of the cyclic group generated by A by the definition, because this set, the cyclic group generated by A, contains all powers of A. In particular, it contains these powers of A, these powers of little a, which constitute big A. Okay? So in fact, every element of big A is also an element of the cyclic group. So big A is contained in the orbit or cyclic group generated by little a. And it follows, because we have inclusion both ways, cyclic group contained in big A, big A contained in cyclic group, that big A is equal to the cyclic group, so the order of big A is equal to the order group of the cyclic group generated by little a. All right, so let's move on to part D. D says if m and k are integers in Zn, and m is not equal to k, show that a to the m is not equal to a to the k. All right, so I've got two different integers, both in Zn, so that means they're integer between 0 and n minus 1. Could be 0, could be n minus 1, but in that range from 0 to n minus 1. And if I have two different integers in that range, then I have two different powers when I raise a to the 2 powers. Now what that's actually going to show, if you see, that's going to show that all of these numbers here in big A are different. All of these results here are different, because if I have a power that's between 0 and n minus 1, I always get different results for different powers. So that's kind of looking ahead, but this is what we want to show in this part, that a to the m is not equal to a to the k if m is not equal to k. All right, so let's go down and see how that works. Prove by contradiction. Suppose that m is not equal to k, and they're both in Zn, and a to the m is equal to a to the k. Now, that's what I'm saying is not true, so I'm supposing the contrary of what I want to prove. So without loss of generality, that's what this means, without loss of generality, we can suppose m is greater than k. All right, either m is greater than k or k is greater than m. If k is greater than m, you just switch them around. All right, then I can multiply both sides of this by a to the minus k. I've just substituted the a to the m for a to the k here because they're equal. And then I do some exponent rules. If I multiply these two, I can add the exponents, m minus k. If I multiply these two, I can add the exponents, k minus k. That gives me a to the 0, which is the identity. So that tells me that a to the m minus k is the identity, right? But m and k are both between 0 and n minus 1, and m is bigger than k. That means that if I take m minus k, the result is bigger than 0, since m is bigger than k, and it's less than or equal to n minus 1 because m is less than or equal to n minus 1. So this difference, m minus k, is between 0 and n minus 1. Okay. Now, since the order of a is n, or n is the smallest positive integer, such that a to the n is the identity. Okay. So if I have a to some number is the identity, that number must be bigger than n. But here I have m minus k, which is smaller than n. This is a contradiction. Okay, this contradiction establishes that this suppose cannot be true. So if m is unequal to k, and they're both in Zn, then a to the m is not equal to a to the k. So this suppose cannot be true, right? So that's what I've shown here. Okay, so this gives me my contradiction. Okay. Now finally, I need to show that the order of A is equal to the order of big A. Right? So let's see. So what I need to show here is, let me get my bearings here. The order of A is n, right? And I've just shown that all the elements in this set are distinct. These are all the elements of A. All the elements of A are distinct, so the number of elements in big A is n. But the number of elements in big A is equal to the number of elements in the cyclic group generated by little a. That follows from part C. Look up here, part C. The number of elements in A is equal to the number of elements in the cyclic group generated by little a. Right? So I've shown that n is equal to the order of big A. The order of big A is equal to the number of elements in the cyclic group, so that tells me that n is equal to the number of elements in the cyclic group. We're done. Go get a cup of coffee.